Let me now show you how important it is to have more than one study on the effect of a treatment on an outcome. So that's the third point of this lecture. We start with saying that each study provides a noisy signal, and the noise depends on the power of a study. And now the issue is that having more than one study really helps us to clarify the signal. And this is not a trivial point, because replications, so doing another study about the same treatment, were extremely rare. They still are, although they are becoming less so, as this graph shows. Still, replications are not too popular among most applied microeconomists, for reasons that I will not discuss here. Now, there's a nice review article in the Journal of Economic Perspectives by Kaufman and Niederle, in which they also discuss the importance of replications, and they come to the following conclusion. They say, we argue that even with modest amounts of researcher bias, which is something that we'll cover in the next clip, or modest amounts of poor replication attempts, replications correct even the most inaccurate beliefs within 3 to 5 replications. So we get closer to the truth, even with all kinds of distortions in the way researchers go about their work with multiple studies. And that is something that we can easily show within the framework that we discussed already, which is based on Ioannidis 2005. And again, we keep it simple, that the question is, does the treatment work or not? We started with a prior of 0.1, then with a well-powered study. If you are able to reject the null hypothesis of no effect, you adjust that to 0.64. If you do another study that is also well powered, then you adjust that and you do again find a statistically significant effect, then you adjust that to 0.97. So basically you're virtually certain that the effect is true then, right? So with just one more study, we have very solid policy advice. And it makes sense to do such replications, because a single study only gives, you can only learn so much from a single study. So ideally, we start with a prior, you do one study, you update that, you have your posterior belief, you do a second study, etc. And if necessary, a third study. But if you have a well-powered study, then you learn pretty quickly, and you may only need 2. That is about whether treatment works. Now, another issue that is also very important is whether how much the treatment works. So what is the effect size? And what can we learn about the effect size based on multiple studies? Obviously those estimated effect sizes vary. There's the distribution again that I showed you earlier. And let me now show you 2 scenarios and see what we can learn from those 2 scenarios. Say that in the first scenario we find we find a statistically significant effect in one case. So say that is a study that you find in literature, and then you do your master thesis and you do not find a statistically significant effect as well, but your point estimate is very similar. So are those 2 conflicting results? Rhetoric question, right? they're actually very much in line with each other. Whereas if in the case that you have two statistically significant findings, but the point estimates are completely off, then those studies are not in line with each other, right? That they actually come with very different conclusions. So the point here is that we should not only focus on being able to reject the null hypothesis of no effect when we're interested in the size of an effect. How are we to combine multiple studies and see what we can conclude about the size of a treatment effect? We can do that by way of meta-analysis. That synthesizes the findings of multiple research studies, and the basic way of thinking about it is that you collect a whole range of studies within a certain area. You standardize those findings, and then you compute a weighted average. And the weights of each study is generally the sample size of that study, because that is a very important determinant of statistical power. And obviously statistical power says a lot about how much you can learn from a study. So say that you conduct such a meta-analysis, then and you find many differences. Those differences then do not only reflect sampling error, that is related to not having an infinite sample size, but it may also relate to the context of the study. If you conduct a study in Sweden and in Italy, then most likely there are differences there. And if you have a sufficient number of studies, then you may be able to see how much of the variation in the reported effect sizes can be explained by a certain moderator. So a contextual factor, a moderator that affects the strength of the effect of the treatment on the outcome. Computing a weighted average is something that we can all do, but doing a proper meta-analysis goes beyond our course. So that would really demand a separate course, unfortunately. Now here's an example, the example that I actually showed you earlier of a meta-analysis in the economics literature. Now, and thinking about effect sizes is very important. So we should not only focus on whether the treatment works or no, but also how much does it work? Because if we have a clear idea of the effect sizes that we can expect, then we can also, for instance, do a cost-benefit analysis. We can see whether the costs are worth or whether the benefits are worth the costs. Now, so that when we take that perspective on econometric work, then we're also going to report our results in a different manner. On the left, in the left column, we have sort of the traditional approach, which is totally focused on p-values. The starting point is then the null hypothesis of no effect. Then you estimate your model and you report your p-values, and then you apply your simplistic decision rule. If I have a p-value of 0.05 or lower, then I say, hey, the treatment works. I have evidence of an effect, and if it doesn't, then the treatment doesn't work, right? So it is as if only findings with a p-value of 0.05 or lower count. If you take sort of more the Bayesian perspective, then you start with a prior based on previous literature, probably informed by interviews with people in the field, and so you have a certain idea of the effect size that you may expect. Then you estimate your model, and you not only report the p-value, but you also report in your conclusions, in your abstract, in your discussion. So what's your point estimate, and what is the confidence interval around this point estimate? In your discussion, you compare that to the prior that was informed by previous research. And you also report statistical power, because that greatly tells us how much we can really learn from your study. And so when you take this perspective, then you focus on what you contribute to what we already knew. So what do we learn given your prior? And for that, all findings count, not only statistically significant findings. So, to make this very concrete, how are you going to report your findings in your master thesis? Well, two scenarios, a statistically insignificant finding and a statistically significant finding. The sentence that I typically find in master thesis of students that do not really think too long about this is, unfortunately, I do not find an effect of number of miles on driver stress levels. And a better way of phrasing this is as follows, and my results suggest a 0.43 increase in driver stress levels given a 1 unit change in number of miles. Nonetheless, a difference in the outcome ranging from 0.02 to 0.88 increase is also reasonably competitive with our data given our assumptions, and the 0.02, 0.88 range is actually the 95% confidence interval. If you find a statistically significant effect, then you do not limit yourself to saying, for example, as expected, I find that a number of hours affects driver stress levels, but you follow a very similar type of reporting of your results. Blah, blah. I'm not going to repeat that, but as you may note, the way we report statistically significant and insignificant findings is similar, actually. So we point out the point estimate and we say what the confidence interval is, and because that is really what we really learn also from your results, beyond the fact whether your p-value happens to be very low, i.e. we should not push aside statistically insignificant findings. If you have a statistically insignificant finding, it basically means that your confidence interval also includes 0, but that does not mean that your study is completely uninformative. Now, ideally, I would teach you how to update the prior about the size of an effect, which is a range rather than a point, how to update that after having conducted your own empirical study, but that would require teaching a lot of Bayesian statistics, and that would go too far, unfortunately.